Hi, I'm Akshat, and today I'd like to talk to you about a really cool and really interesting procedure that is surface photovoltaic spectroscopy. So let's just start and get into it. The first question is, why do we need this, right? What's the motivation behind it? We know semiconductors are made of electrons, holes, and a wide arrangement of them, right? However, those are not ideal. We have certain geometries that we have associated to these things, but it is not necessary a semiconductor has to follow them always. There may be some defects, some sort of anomalies, some features that are really interesting that cause a change in its behavior. And how do we actually get that information? We can't, just break it apart and look into it. That's not really helpful. So we need some other methods. Now, a semiconductor consists of more or less two parts, you could say. The first one is the bulk, which is this portion right here that is deep below the surface. And the second is the surface, which is the top layer, or roughly the top two or three, or somewhat less. So the traditional methods that have existed for a long time, what they do is they give a lot of information about the bulk of the semiconductor, that is this inner aspect. But they don't really talk about, and they aren't able to tell you much about the surface, how that is changing. Now, why do we want to know what the surface has? The surface has a lot of cool physics ingrained in it, such as dangling bonds, defects, band bending, and trapped charges. Now, these things have a lot of applications in solar cells, optoelectronics, a lot of fields. And the thing is that all of these applications depend on the surface properties. So the motivation behind SPV is this. Well, how do we actually extract this information? And what SPV does is it uses light. Now, how does it use light? Let's say I take a semiconductor, right, and I shine light on it. Now, we know light consists of photons and it has energy. Each photon has an energy associated with that is h nu. Now, so when this photon strikes this surface, it releases an electron, as we know from the photoelectric effect. What happens is, if this h nu is greater than the band gap, an electron will be released. That's simple enough. But that actually creates electron hole pairs in this semiconductor, which causes a change or which induces an electric field, which further changes the distribution of charges. And what this distribution does is it causes a change in the separation of the energy levels. And when we have this change in energy levels, we have a reduction in the band bending. And this is something you can measure, which gives you how the surface is changing. So for example, in this, let's take the first example of an N-type semiconductor. So we have this valence band, and initially at this separation level, this was its energy. What happens is when we shine light on it, it actually dropped down. When it dropped down, this Be changed to Be prime, which corresponds to a change in the energy level. So we can actually monitor this, we can actually measure this, and that gives us information. However, this is only for a singular point. We have shined light on a singular point. What if we have to figure out the the stuff about all the points? We create a lot of data. Before we get into that, this is a mathematical description of it. So how do we actually, mathematically model this? So we assume that the semiconductor has some surface charge density Qs. Now, if it has some charge density, then this will act like a capacitor, because A epsilon upon D, that gives you the capacitance. But the other formula will be del Qs by del V. When you shine light on it and the energy was greater than the band gap, what happened was there was a change in the surface charge density. Let's assume it was del Q. So what happened is, when there was a change in del Q, we can actually record it. We have a way of measuring it by the voltage. We know the del V will correspond to del Q upon C, and this is something we can measure. And once we have measured this, we know how to interpret this data. For example, let's take a very simple example, very simple graph that, let's say, this is the result of an SPV measurement that we took. Now this SPV measurement, it has a single point. If you observe, there are three primary things that you can consider, that you can take out from this graph: band gap onset, excitonic peak, and defects. Talking about the first one, band gap onset. So let's say I have shined electrons upon it. And at this point, at this particular energy level, that is roughly 1.5 electron volts, we see a sharp increase in SPV. Now, this is the point, that is the band gap of that semiconductor. However, it is the band gap of that particular point. It is not necessary that every single point at the surface will have the same band gap. For that, we will have to do a measurement on the entire surface, on lots of points on that semiconductor, and then measure it. So you could construct sort of a 3D map of how the band gap is varying with respect to the X and Y coordinate system. The second thing that is really cool is this peak that you get right before the onset. That is the excitonic peak. And the third one is defect states. Now, defect states simply means that, let's say we have the surface and we shine light on it. It is not necessary that only the top layer of electrons will be ejected. It is also possible that the second layer or the third layer also have electrons that get released. And these can be measured as tiny fluctuations in the voltage, and that is measured as defect states. For example, this one at roughly 1.1 electron volts, this one as 1.24 or 25 electron volts are examples of defect states. The second cool thing is semiconductor heterojunction. What does this mean? Let's say I have two semiconductors, A and B, and I join them. At this boundary of the two semiconductors, there will be some interesting phenomenon that we don't really have any way of predicting right now. Let's say. So what happens is there will be some band discontinuity at this edge. How do you measure that? Because there is not really any traditional measurement of measuring at the surface. So let's say we consider it a single semiconductor and we conducted an SPV measurement at that instant. So what you can observe is there are actually three different sections of the graph. The first one is this zero line, which corresponds to nothing. We don't really have any interpretation of that. The moment we get the first sharp increase, that corresponds to the first semiconductor band gap. Then when we get this sudden sharp rise, that means that this is the point where it is offsetting. This is the band discontinuity. And when you go further ahead, you get the second band gap of the second semiconductor, that is about 1.6 electron volts. And so this can give you a lot of information about how we actually have a junction of two different semiconductors. And depending on further analysis and further interpretation of the graphs, you can also determine the type of heterojunction. For example, P or N or P, PP or NN, stuff like that. So we have so far I have talked about a lot about the actual implementation and interpretation, but what is it without any applications, right? And this is a lot of applications. The first one, that is photovoltaic cells. Sorry, photovoltaics. This is just an application of how band gap and the defects of the surface can be used in solar cell materials. The second could be heterostructure interfaces, as we just talked about. We have a method of telling how band aligns and how interface energy changes. We can just use this method by tracking how photocarriers are moving across materials. The third one is thin films and nanostructures. Now we have shined light on it, so it is not destructive. It can be used for extremely thin files and measuring their properties. The last one is photoelectrochemical cells, which is simply, instead of using two semiconductors, we have a semiconductor and an electrolyte interface. And when we probe charge transfer at that boundary, we can get an application for that as well. Now, talking about the advantages and the limitations, because obviously we'll have both of them. Now, one of the best advantages is that it directly probes the surface. This is one of the very few methods that can achieve this. However, it also comes with a limitation that it is obviously strongly sensitive, surface sensitive, and we don't really have any bulk information. But I think that is a fair enough trade-off. The second advantage is it is non-destructive and can be contactless. What does this mean? We are not using any physical contact on the surface of the semiconductor. We are using light. So it is not actually harming or causing any physical change to the system that we are trying to measure. This is the farthest that we can get to pure observation without actually causing any perturbation to the system. However, it has limitations as well because it requires very careful interpretation, because there will be a lot of overlapping readings due to band tails or traps or excitons, or maybe even the photons readings are a bit off. Another advantage is that it is sensitive to sub-band gap transitions, for example, that we talked about here, these defect states. This is also something that we can map. However, the signal is reduced. Why? Because we have a lot of strong surface recombination. Another advantage is that it can resolve bandages, excitonic features, and defect levels. And the last limitation is that quantitative analysis depends on accurate modeling of band bending and capacitance. If somehow the capacitance is not accurate, then this will give extremely misleading results. So, in summary, this is what an SPV machine actually looks like. This is the laser that is used to shine light, and this is how voltage readings are measured. So just to summarize what we talked about today, surface photovoltaic spectroscopy, it measures the illumination induced charges. The charges or the potential or the current observed in a semiconductor after you shine light on it. What does this tell us? It tells a lot of information about the surface states. It tells us a lot about the defects of the system, and it tells us a lot about the recombination process. SPV is extremely surface sensitive but contactless and non-destructive, making it a very powerful tool for characterizing thin films that are sensitive to destructions if you use any physical methods, and also heterostructures. Overall, as an ending note, SPV can connect optical absorption, that is the photoelectric effect, with electrical responses, that is the observation of the voltage. And this bridge, this sort of acting as a bridge between these two paradigms, this makes it a really important method in semiconductor research. And I hope you had some interest, and I hope this was interesting to you. Thank you.